All right, want to pick up where we left off from the last video. So one more practice problem with assigning oxidation numbers. We're looking at H2SO4, and let me actually get a little bit more space here. There we go, just a little bit. Okay, so H2SO4, we actually have three elements we need to account for. So we got hydrogen, we got sulfur, and then we got oxygen. Okay, and once again, we want to assign the oxidation numbers for each of those elements. So always start off by, number one, identifying that H2SO4 is a neutral compound. So everything should add up to be 0. The next thing is ask yourself, of those three elements, which ones do we have rules for? We actually have rules for hydrogen and oxygen. So the rule for hydrogen is it's always positive 1 unless it's a metal hydride. It's not a metal hydride, so hydrogen is going to be plus 1. I also know a rule for oxygen. Oxygen's always going to be negative 2 unless it's bonded to fluorine or a peroxide. In this case, it's neither. So that's the oxidation number there. And then we're going to do a little math to figure out what the oxidation number should be for sulfur. So to do that, I'm going to write H2SO4 out here to the side, get a little bit larger. Okay, we already figured out that hydrogen is plus 1. There are 2 hydrogens, so that means a total of plus 2. We also figured out oxygen's negative 2. There are 4 of them, so that means it's got a total of negative 8. And the total between hydrogen, the questionable sulfur, and oxygen all need to add up to be 0 because H2SO4 is a neutral compound. So what number plus 2 and negative 8 would be 0? And the answer is positive 6. Now that positive 6 is the total for sulfur. That has to be divided up over the total number of sulfurs, which is just 1. And so that means sulfur's oxidation number is indeed plus 6. And so plus 6 would be the oxidation number there. Just for argument's sake, what if sulfur was, let's say, 2? Like, what if there were 2 sulfurs, for example? Because I know we haven't really seen any examples where that was the case. Well, then in that case, that positive 6 is divided up over 2 sulfurs. So that means the oxidation number for sulfur would be positive 3. And that would be the answer here. Okay, but that's not the case. Okay, I don't want to confuse anyone. That was just an example of what you would do. But like I said, it's just 1 sulfur, which means it's positive 6 is the oxidation number. And that would be the answer right there. Okay, so how do we use all this information? How is this going to help us with a redox reaction? Well, now that we understand how to assign oxidation numbers, let's take a look at actually what happens in a redox reaction. Let's consider the single replacement reaction that I have right here. When you have zinc, solid zinc, and you drop it into copper 2 chloride solution. Well, hopefully you'll be able to predict the products. That's a review of topic 9, but what's actually taking place? What's happening? Well, remember that aqueous, okay, this aqueous means that it's dissolved in solution. So this CuCl2, what that actually means is you have some copper ions, okay, copper 2 plus specifically, and then you've got some chlorine ions. And then over here, you have solid copper as a product, and you've ended up creating a zinc chloride solution. So you end up having zinc ions and then some chlorine ions. Okay, so notice how the chlorines don't change from the reactant side to the product side, right? You have chlorine ions on the left, you have chlorine ions on the right. Nothing happens with them. So remember, what do we call those? Those are spectator ions. So we don't really care about chlorines. Chlorine's not actually doing anything in this reaction. And so if you notice, that's why down here, I've just simplified it by removing the chlorines, okay? Because chlorine is a spectator ion. Now notice what happens. Zinc went from neutral, okay, it's got a charge of 0. It went from neutral to now being plus 2. And copper went from being plus 2 down to being neutral. Do you see how their charges are changing? That's how you know you have a redox reaction, okay? More specifically, we can actually show what's happening with what's known as half reactions. Half reactions, by the name of it, is it's showing half of the reaction. So notice one substance is increasing in charge while the other thing is decreasing in charge. And so we show both of those halves with a half reaction. If you take a look at zinc, okay, zinc went from 0 to +2. Why would zinc go from being neutral to +2? What's the difference there? Well, remember what a redox reaction is it's a transfer of electrons. Specifically with zinc, zinc must have lost 2 electrons, right? That's why it went from 0 to +2. It gave up those 2 electrons. Well, those 2 electrons have to go somewhere, right? So where do they go? The copper 2+ ion, it took those 2 electrons that were just kind of floating out there, and it actually took them, and as a result, that's what brought its charge down from +2 down to 0. Do you see how that happens? Think about it like this. When you go to a store and you buy something for $20, okay, that's one transaction, okay, just like there's one chemical reaction. But there's 2 parts to it. Someone is losing money, the customer. Someone is gaining the money, the store or whoever is, selling, right, the seller. So think about it like that. Redox reactions, that's 2 processes happening at the same time, and the half reaction shows that. If I were to do the half reaction model for, like I said, to go into the store, my half reaction would be, oh, I lost $20. And then there would be another reaction, the seller, oh, I gained $20. And then together, that represents the whole transaction, if that makes any sense. So that was just showing you an example of what's going on in a redox reaction, and more specifically, showing how the charges are changing and why. Okay, here's a pictorial view of what I just showed you. So for example, the zinc and the copper solution. So this right here is a solid zinc bar. So if you can see right here, I know it's kind of small, but those are solid zinc atoms. And in solution right here, you've got your copper ions. Well, here's where those 2 electrons are being transferred. And if you leave it long enough, what ends up happening is this bar is actually now going to be plated with solid copper, and what's going to be in solution here ends up being the zinc ions. And in lab, we actually can show this. There's some reactions that we do. Normally we would have done this in the lab, but because of the situation, you could see a video. But there's a lab that we do, or an experiment we do, where we have a copper wire and we dip it in silver nitrate solution, and you can see actually the copper wire gets a little fuzzy, and it's because it's doing that replacement. Okay, so this is where you get those terms oxidation and reduction, right? So redox reaction is an oxidation reduction reaction. Oxidation, the process of being oxidized, is whatever substance is losing the electrons. And remember, if you're losing electrons, negative particles, that means your charge is increasing. Your charge is going up. But whatever's being reduced is gaining electrons. And if you're gaining electrons, that means your charge is going down. So a way to remember that is you can think of oil rig. Oil rig is a mnemonic device, a way to remember. So oil rig stands for oxidation is losing electrons. Reduction is gaining electrons. That's one way to remember it. So revisiting our problem that we just saw a few slides ago, remember zinc went from 0 to +2, and that's shown down here, more specifically 0 to +2, right? Well, zinc's charge went up as a result of losing those 2 electrons, right? So zinc is what was oxidized. So if I asked you what was oxidized, that's zinc. And then copper went from +2 down to 0. So its charge went down because it gained 2 electrons. So if I asked you what was reduced, the answer there would be copper. Finally, there's the terms oxidizing agent and reducing agent. Okay, let's not make this more difficult than it has to be. Okay, I'm going to put OA for oxidizing agent, RA for reducing agent. Okay, the oxidizing agent is simply the reactant that causes oxidation, and the reducing agent is simply the reactant that causes reduction. So, like I said, let's try not to confuse this. Let's make it as simple as possible. Whatever is oxidized is the reducing agent. They're always opposites, and whatever was reduced is the oxidizing agent. But the key thing here is you need to make sure you write them however they came as reactants. So for example, zinc we said is oxidized, so it's the reducing agent. But how did zinc come as a reactant? Well, it just came as zinc, right? It was just zinc. So it's okay to just put Zn as the reducing agent. Zinc was the reducing agent. Well, copper was reduced, and therefore it's the oxidizing agent. But how did copper get written as a reactant? It wasn't just copper, it came as copper 2 chloride, CuCl2. So I need to make sure I write down CuCl2 as my agent. So as a reminder, just the elements get written when we ask what's oxidized and reduced, but the agents, okay, that needs to be written how it came as a reactant. All right, with that, I'm actually going to stop this video here, and we're going to do the redox reaction examples in the next video.